Nearly 3 billion miles from Earth, something on Neptune is behaving in a way that has genuinely surprised the scientists tracking it, and it isn't a single event. It's two separate, ongoing mysteries, both confirmed through years of careful observation, both still unresolved as of 2026, and both centered on a planet that, until recently, most people assumed was simply a cold, quiet, unchanging ball of blue gas sitting at the edge of the solar system. It isn't quiet. Its atmosphere has been cooling dramatically for reasons nobody has confirmed, and its storms, enormous, swirling dark vortices wider than entire oceans, have started doing something scientists didn't expect at all: reversing direction, breaking apart unpredictably, and shrinking out of existence in ways that don't match any of the models built to describe them. None of what follows requires exaggeration to be worth taking seriously. This is what NASA's own Hubble and Webb telescope teams have actually documented, in their own words, published in their own peer-reviewed research. This is the story of what's genuinely currently happening on Neptune, and why, even with two of the most capable space telescopes ever built watching it closely, scientists still don't have a full explanation for either mystery. To understand why these findings matter so much, you first have to understand just how little we've ever really known about Neptune, and how recent and how limited our ability to actually watch this planet change over time has been. Neptune is the outermost of the 8 major planets in our solar system, orbiting the Sun at a distance of roughly 8 billion miles, so far out that a single orbit takes about 165 Earth years. Only one spacecraft in history has ever visited it directly. NASA's Voyager 2 flew past on August 25, 1989, capturing a single, brief snapshot of the planet's atmosphere before continuing on its journey out of the solar system entirely. Everything scientists have learned about Neptune since that flyby, more than 3.5 decades ago, has come from telescopes observing the planet from a great distance. First, the Hubble Space Telescope, launched into orbit in 1990, and more recently, the James Webb Space Telescope, which began observing Neptune in 2022. That gap between a single historic flyby and everything learned since matters enormously for understanding why Neptune's ongoing changes have taken scientists so long to fully appreciate. Voyager 2's 1989 encounter revealed, among other things, a massive, dark, oval-shaped storm in Neptune's southern hemisphere, roughly the size of Earth itself, which scientists at the time named the Great Dark Spot, drawing an obvious comparison to Jupiter's own famous, long-lived Great Red Spot. But unlike Jupiter's storm, which has been continuously observed for at least 2 centuries, and maybe considerably older still, nobody had any way of knowing at the time how long Neptune's own dark spot might last, or whether it represented a permanent, stable feature of the planet's atmosphere at all. The answer to that question arrived only a few years later, and it came as a genuine surprise. When Hubble turned its own instruments toward Neptune in the mid-1990s, not long after Voyager 2's flyby, the great dark spot that had seemed like such a defining, dramatic feature of the planet's atmosphere had simply vanished. According to NASA's own account of the observation, astronomers hadn't necessarily expected it to still be there, but its complete disappearance within just a few years still came as a notable finding. An early hint that whatever process drives these dark storms on Neptune, it behaves nothing like the remarkably stable, centuries-long storm system observed on Jupiter. That pattern of dark storms appearing, persisting for a while, and then eventually disappearing has continued to hold up across the decades since, thanks specifically to a long-running Hubble observation program called Outer Planets Atmosphere Legacy, or OPAL, which provides detailed yearly global maps of the solar system's outer gas giant planets, allowing planetary scientists to track exactly this kind of long-term atmospheric change in a way that simply wasn't possible before this kind of sustained, repeated monitoring program existed. Using OPAL data, along with archived observations dating back to Voyager 2's original flyby, researchers led by Michael Wong at the University of California, Berkeley, along with collaborators including Amy Simon and Andrew Hasu, have identified a total of 6 distinct dark spots on Neptune over the decades since 1989, each one eventually fading and disappearing, typically lasting somewhere between 2 and 6 years before vanishing entirely, with new ones tending to form somewhere every 4 to 6 years on average. Here's where things become genuinely, actively puzzling, rather than simply an interesting, settled pattern. In 2018, Hubble detected a new dark storm forming in Neptune's northern hemisphere, a vortex wider than the Atlantic Ocean, roughly 4,600 miles across. Researchers began tracking it closely, and in 2019, observations showed the storm doing exactly what earlier storms had generally been expected to do: drifting steadily southward toward Neptune's equator, a region where these dark spots are typically expected to break apart and vanish from view entirely, based on the general behavior patterns established across the previous several decades of observation. Then, in August of 2020, the storm did something nobody had specifically predicted. According to NASA's own published account of the observation, rather than continuing its expected drift toward the equator and its likely dissolution there, the vortex abruptly changed direction entirely, doubling back and drifting north again, away from the equator, in a way that directly contradicted the pattern researchers had come to expect based on Hubble's decades of prior tracking. At the same time this direction reversal occurred, Hubble also detected a second, smaller dark spot appearing nearby, informally nicknamed Dark Spot Jr., measuring roughly 3,900 miles across, positioned specifically near the side of the larger storm facing the equator, precisely the kind of location where some computer simulations had suggested a disruption or fragmentation event might occur. Researchers suggested this smaller companion spot might represent an actual fragment that had broken away from the larger storm as part of whatever disruption process was underway, though the exact mechanism remained and still remains genuinely uncertain. Coverage of this finding at the time captured the researchers' own candid reaction to what they were seeing. As reported by Fox News following the observation, the storm's unexpected reversal left experts, in their own words, without answers, changing direction in a manner unlike any of the other dark spots that had previously been tracked on the ice giant. Michael Wong, commenting on the smaller, newly appeared fragment specifically, described the team's genuine excitement about these observations, noting that this smaller dark fragment was potentially part of the larger dark spot's ongoing disruption process, an event they were fortunate enough to be actively watching unfold in real time rather than reconstructing after the fact from incomplete data. That storm's story didn't end there. Continued monitoring through Hubble's Opal program has tracked this same dark vortex over subsequent years, and in a research presentation delivered at the American Astronomical Society in October of 2024, researchers documented what they described as the dissipation phase of this same storm, tracking its gradual shrinking over an extended observation period. According to reporting from Spacecom covering this ongoing monitoring, the storm, once large enough to stretch from roughly Boston to Portugal, has been steadily dwindling, shrinking from approximately 3,100 miles across its long axis down to roughly 2,300 miles over the course of Hubble's multi-year observation period, and what researchers describe as the first time they've been able to closely track an entire dark spot's demise from beginning to end in this kind of continuous, sustained detail. Wong, reflecting on the broader significance of being able to track this behavior so closely, noted directly that no facilities other than Hubble and the original Voyager 2 flyby decades earlier have ever observed these vortices in this kind of detail, meaning that for the foreseeable future, Hubble remains essentially the only tool capable of providing the sustained data researchers need to understand just how common or how genuinely erratic this kind of storm behavior actually is on Neptune. There's a broader scientific puzzle embedded in all of this that's worth drawing out explicitly, because it connects directly to a deeper question about what's actually happening far beneath Neptune's visible cloud tops, in parts of the planet's atmosphere no telescope has ever been able to observe directly. These dark spots are believed to be a specific type of storm called an anticyclone, forming in regions of high atmospheric pressure, in contrast to storms here on Earth, which typically form around low-pressure regions instead. As these storms spin, they're believed to pull up darker material from much deeper within Neptune's atmosphere. Material that researchers suspect may include hydrogen sulfide, the same compound responsible for the distinctive, unpleasant smell of rotten eggs here on Earth, though that specific composition remains itself an area of ongoing study rather than a fully settled conclusion. In a related and genuinely fascinating piece of research published in 2019, the same team led by Amy Simon, alongside Wong and Xu, discovered something that added yet another layer to this puzzle. While analyzing archived Hubble images tracking a smaller, separate dark spot that had appeared in 2015, researchers noticed small, bright white clouds forming in the same general region of Neptune's atmosphere, roughly 2 years before the larger 2018 Great Dark Spot itself became visible, clouds that then measurably lost some of their brightness right around the time the larger dark storm actually emerged. According to the researchers' own published conclusions, this timing suggests that Neptune's dark spots may actually originate from considerably deeper within the planet's atmosphere than scientists had previously assumed, with these bright, high-altitude companion clouds made of methane ice crystals, forming above the storm the way lenticular clouds cap the peaks of tall mountains here on Earth, offering an indirect but genuinely valuable clue about activity happening in parts of Neptune's atmosphere that remain otherwise completely invisible to any telescope. That's one genuine ongoing mystery. Storms that don't behave the way established patterns suggest they should, reversing direction, fragmenting unpredictably, and offering indirect hints about deep atmospheric activity, scientists still can't observe directly. The second mystery, discovered more recently and confirmed just last year, involves something considerably more fundamental. the actual temperature of Neptune's atmosphere itself. In March of 2025, a research team led by Henrik Mellon of Northumbria University, using observations gathered by the James Webb Space Telescope in June of 2023, confirmed something genuinely surprising about conditions in Neptune's upper atmosphere. The primary goal of that observation had been to finally confirm the presence of auroras on Neptune, a phenomenon already well documented on Jupiter, Saturn, and Uranus, but one that had eluded confirmation on Neptune specifically for more than 3 decades, despite repeated attempts using some of the largest telescopes on Earth. Using Webb's near-infrared spectrograph, the team finally detected the specific chemical signature, a molecule called trihydrogen cation, that confirms auroral activity is indeed occurring in Neptune's atmosphere, just as theory had long predicted. But alongside that confirmation, Webb's data revealed something nobody had specifically gone looking for. For the first time since Voyager 2's original 1989 flyby, scientists were able to directly measure the actual temperature of Neptune's upper atmosphere. And what they found was, in the researchers' own words, a genuine surprise. According to the published findings, Neptune's upper atmosphere in 2023 measured at just over half the temperature Voyager 2 had recorded during its flyby more than 3 decades earlier, representing a drop of several hundred degrees Fahrenheit. That cooling helped explain part of why Neptune's auroras had proven so difficult to detect for so long, since colder atmospheres generally produce considerably fainter auroral activity. But it raised an entirely separate, unresolved question of its own. Why did Neptune's atmosphere cool so dramatically in the first place? As reporting on the discovery from the Smithsonian magazine put it directly, that specific question doesn't yet have a confirmed answer. And researchers involved in the study have suggested it may only be resolved through further continued observation. It's a genuinely puzzling result specifically because Neptune sits more than 30 times farther from the Sun than Earth does, completing a single orbit only once every 165 years, meaning any expected gradual seasonal temperature change should, in principle, play out over a timescale of many decades, rather than the roughly 3.5 decades separating Voyager 2's flyby from Webb's newer measurements. A cooling shift this substantial, occurring within that comparatively short window, doesn't fit neatly within the kind of slow, predictable seasonal pattern researchers might otherwise expect from a planet orbiting so incredibly far from the Sun. According to NASA's own description of the research team's future plans, astronomers intend to continue using Webb to study Neptune's atmosphere and magnetic field over an extended period, ideally spanning a substantial portion of the Sun's own roughly 11-year solar activity cycle, since solar activity is already known to influence upper atmospheric conditions on other giant planets throughout the solar system, and may well be playing some role in Neptune's own temperature behavior as well. Whether that continued observation eventually reveals the Sun's activity cycle as the driving factor, or points towards some other, entirely different mechanism, remains, as of 2026, a genuinely open question. Put both of these ongoing mysteries together, storms that reverse direction and fragment in ways existing models don't fully explain, and an atmosphere that's cooled dramatically for reasons scientists haven't confirmed, and you get a picture of Neptune that looks considerably less like the quiet, static, frozen world many people still imagine it to be, and considerably more like an actively dynamic, still poorly understood planet, one that continues to surprise the very researchers who've spent decades specifically studying it. It's worth being honest and direct about what these two mysteries do and don't and actually represent, since that honesty matters far more than any dramatic framing built around them. Neither of these findings suggests anything supernatural, anything dangerous to Earth, or anything that violates known physics. Storms forming, evolving unpredictably, and eventually dissipating is a completely normal part of how giant planet atmospheres behave. What's genuinely notable here is simply that Neptune's specific storm behavior doesn't yet match the models researchers built based on decades of prior observation, meaning those models still have real, meaningful gaps in them. Similarly, an atmosphere cooling over time isn't inherently mysterious in the abstract. What makes Neptune's specific case notable is the scale and apparent speed of that cooling relative to what a planet at its extraordinary distance from the Sun would typically be expected to experience. What both mysteries genuinely represent is something considerably more interesting than manufactured alarm. Clear, direct evidence that even after more than 3.5 decades of study, following a single historic spacecraft flyby and years of careful, sustained telescope observation, since Neptune still has fundamental aspects of its behavior that scientists haven't fully figured out, that's not a failure of the research. It's a reflection of just how difficult it genuinely is to study a planet nearly 3 billion miles away using instruments based here on Earth or in orbit around it. And a reminder that even planets we've technically visited once and photographed repeatedly since can still hold on to genuine unresolved secrets about how they actually work. Researchers aren't simply waiting passively for these mysteries to resolve themselves. Hubble's Opal program continues its yearly monitoring of Neptune's atmosphere, tracking any new dark spots that emerge, and watching closely for further unexpected behavior like the direction reversal observed in 2020. Webb's team, meanwhile, has committed to continued observation of Neptune's magnetic field and atmospheric temperature across an extended stretch of the Sun's own activity cycle, specifically to determine whether solar activity plays a meaningful role in the planet's ongoing atmospheric cooling. Both efforts represent exactly the kind of patient, sustained, methodical science that these particular mysteries actually require, rather than any single dramatic observation capable of resolving either question all at once. Nearly 3 billion miles from Earth, right now, Neptune's atmosphere continues doing something scientists are still working to fully understand. Somewhere within its clouds, a dark storm may be forming, evolving, and eventually fading in ways that don't yet match any existing model. And somewhere in its upper atmosphere, gas that's measurably colder than it was 3.5 decades ago continues cooling for reasons nobody has confirmed. Both of those genuine, ongoing puzzles are exactly why astronomers keep pointing some of the most powerful telescopes ever built back toward this distant, quietly complicated blue world, year after year, patiently gathering the kind of long-term data that might eventually finally explain what's actually happening there. If you want to see what Hubble and Webb continue to reveal about Neptune's ongoing changes in the years ahead, that research is still actively underway right now. Subscribe if you'd like to keep following where it goes.